Okay, so we're continuing here in Chapter 3 of Industrial Organization and focusing on finding more equilibria, right? So we talked about the best way to find sort of a pure strategy Nash equilibrium in a simultaneous game last time. You just underline the best response for each of your opponent's strategies, and then where they're both underlined, that's the mutual best response. So here we are going to focus on mixed strategies. And so mixed strategies are kind of a pain in the butt, but they're important, right? Because a lot of times, if I know what you're going to do and you know what I'm going to do, then there's really no game, right? So you can think about rock, paper, scissors, you can think about chess, etc. And so there needs to be some uncertainty about what the player is going to do, and we think of that in terms of probability in game theory. So we're going to start with the matching pennies game. And so the matching pennies game is where there's two players, you both put down a coin. If they match, then player one gets them both, right? So they net one penny, right? Because they had their own penny, they get the player two's penny. And if they don't match, then player two gets the pennies, and so they net one penny. And so basically you can see, if I'm player one and I know player two is always going to do heads, then I'm going to do heads. And if I know player two is always going to do tails, then I'm going to do tails. Whereas for player two, if I know player one's going to do heads, then I'm going to do tails. And if I know player one's going to do tails, then I'm going to do heads. And so there's no pure strategy Nash equilibrium, right? It's a zero-sum game, just like rock, paper, scissors. There's just only two strategies here rather than three, but it's very much the same, right? And so then the question is, all right, well, how do we find a Nash equilibrium that makes sense? And, it's not going to be a surprise here. But what we want to do is we want to think about what's the best response or reply function, right? And in order to find that, we need to assign some probabilities and then figure out, well, what's the expected payoff based on those probabilities. And so, for player one, what's the probability, that they're going to play heads? So PR1 equals 1 if player one believes that player two will play heads, right? Because then they want to match. And they will do that if they believe that the probability of player two, so PR2 playing heads, is more than 1/2. So we can think of PR1 as the probability that player one is going to play heads, and PR2 is the probability that player two is going to play heads. But player one will play tails, right? If player one believes that player two is going to play heads with less than half probability. But so how do we find that? Well, we need to set up the payoff function. And in order to find the payoff function, we basically want to think, okay, well, player two has all of the same sort of knowledge, right? It's perfect information, it's common information. And so player two is going to choose, heads if they think player one's going to choose tails, and vice versa. They'll choose tails if they think player one is going to choose heads, right? And so obviously right here, it's going to be at that sort of 1/2 for both players, right? And it's not a surprise, right? It's 1/2. There's only two strategies, and the payoffs are symmetrical. And so the only thing that makes sense in this case is playing heads half the time and playing tails half the time. But in order to do that, formally, we need to think about what that's going to be. And so we want to solve for the expected payout for each of the potential strategies, right? So player one, we need to think about, okay, well, what am I going to do if player two does heads with this probability and tails with that probability, and then find my equilibrium. And of course, it's going to be right in the middle where they're both 1/2. So here's the math, and we'll come back to this, in various games that we look at in industrial organization. But we're basically looking for the expected payoff from playing heads, right? And so remember, player one gets a penny if player two plays the same thing. So the expected, what all this means here is the expected profit, right? We usually use pi for profit in economics, at least if we're in microeconomics. It might be inflation if we're in macroeconomics. So the expected payoff for player one of playing heads is equal to the probability that player 2 plays heads times 1, right? That's the payoff, plus 1 minus the probability that player 2 plays heads, so that's the probability that they play tails, times the payoff if that happens, which is minus 1 because player 1 loses their penny. And then we just simplify this a little bit, right? So PR2 times 1, and then this minus minus becomes a positive, so we get 2 PR2s, and then the 1 times the minus 1 becomes minus 1. So the expected payoff for player 1 of playing heads is 2 times the probability that player 2 plays heads minus 1. And then we can do the same thing for tails, right? We just have to remember that if player 1 plays tails and player 2 plays heads, they get minus 1. And then if player 1 plays tails and player 2 plays tails, they get 1. And then we simplify this expression and we get now 1, right? Because it's 1 times 1 minus 2 times the probability that player 2 plays heads. Now, we can do the same thing for player 2, right? And so calculate the expected payoff from playing heads and the expected payoff from playing tails. We get basically the opposite, right? Because now they lose if they match and they win if they don't match. So we get the expected payoff of playing heads is 1 minus 2 times PR1, where PR1 is the probability that player 1 plays heads, and the expected payoff from playing tails is 2 PR1 minus 1. Okay, so that's really confusing, but what we do know is that we should expect the payoffs to be equal, right? And so finding that mixed strategy equilibrium is always saying, okay, we've got these probabilities now. They should be equal. The expected profitability for player 1 playing heads should be the same as the expected profitability for player 1 playing tails, right? And then we solve them. We get 4 PR2 equals 2. Divide both sides by 4, we get PR2 equals 1/2, and then since we know we have symmetry here, we can say that PR1 equals 1/2 as well. And really, that's all we found in the graph, right? It's 1/2, 1/2, that's where they cross. That has to be the mutual best response. But we can find them mathematically, right? And, you know, sometimes it's obvious, right? Like in this game where it's 1/2, 1/2. But if the payoffs are not symmetrical, if there's more than 2 strategies, then it's not necessarily obvious. And so we do have to go through the math. Now, another possibility is that our payoffs are not discrete, right? They're continuous. And so this is going to be the case when we're choosing like price, for example. And so we can do a similar type of thing where it's not about the probability of the different prices, but about a continuous function of the prices. And so here what we have is our lemonade stands. And this is going to come back when we're talking about oligopoly, you know, whether it's, you know, the Cournot model, the Stackelberg model, the Hotelling model. We're going to come back to this. And so here is our profit function. So we've got 2 firms. We've got firm 1 and firm 2. And what this profit function means is that the profit for firm I, that could be 1 or 2, is some function of firm 1's price, PI, and firm's 2 price, PJ. And so it's equal to A times PI minus PI squared. That's a sort of common profit function for price, but then plus PI PJ, right? So if the higher is your opponent's price, then you want the higher to be your price. And basically what we want to do is we want to find the best response for firm I for all the potential values of PJ, right, firm 2, and then do the same thing opposite, right, but they're symmetric, so they're going to be the same. And then we'll have 2 equations with 2 unknowns, and we can solve them. So let's look at that. So here, basically, all we're doing is we're differentiating that profit function in terms of P1 for firm 1, right? Because firm 1 only controls firm 1's price. And so, you know, just taking the derivative, this is a linear term, right? So we just get A. This is a quadratic term, so we get minus 2P1. And then this is basically a linear term again, right? So we just get P2 or Pj. And so this is the derivative with respect to, for firm 1, right? A minus 2P1 plus P2, set it equal to 0 because we're trying to find the maximum. And then here it is for firm 2, A minus 2P2 plus P1. And then set that equal to 0. Now just notice that instead of like the regular sort of profit maximization that we have where it's only our own price that comes into the first order condition, now we have our price and the other firm's price, right? And so now we have two equations with two unknowns and we'll have to solve them. So we can graph them, right? So we graph them in terms of our P1 and P2 space. We can say, all right, well, if, here is our best response for firm 1 for all of the prices based on whatever the price of P2 is. Here is our best response for firm 2, all of the firm 2 prices based on what the firm 1 price is. I mean, the graphs kind of show you that they cross once and that there's sort of one unique equilibrium, but it's not going to necessarily tell you what the answer is, right? In order to do that, we solve our firm 1's best response for P2. So that's equal to minus A plus 2P1, right? That just comes from these first order conditions. Put P2 on the other side and solve. And then we just plug it in, right? So P2 equals A plus P1 over 2. Set them equal to each other. So now we have minus A plus 2P1 equals A plus P1 over 2. Lots of different ways to solve that, but basically what we end up getting is that they set the same price, which is equal to A. And then if we want to solve for the profit, right, now we know that the profit is A, and so we basically get A times A is A squared, minus A times A is A squared. Again, that's 0, but then plus A times A, right? And so that becomes A squared, and that's the profit there. Now, one thing to note perhaps is just that this kind of requires competition, right? If the firms could control both P1 and P2, if they collude, which is one of the things we're going to talk about in industrial organization, then this changes a lot, right? Now you're going to set prices really high depending on the demand curve. And so that's one way we can kind of try to tell if there is some collusion in the market. All right, so we'll stop there. We have one more video for chapter 3, which will finish up our introduction to game theory.